So we just had you look at a little simulation of what happens when you have a tornado and or hear a tornado warning. And then we just sort of asked you, what would you like to know about this tornado, the motion of the tornado? Well, I'll tell you what, if I was actually at my house and I heard a tornado warning like that come across the TV or the radio or the internet, whatever, here's what I would want to know. First of all, where is the tornado now? Like, where is it now? I live kind of over by the Kingsport Aquatic Center and Meadowview and kind of on that end of town. So, where is this tornado? What speed is it moving at? That is important. But what direction is it moving? Is it moving towards me? Is it moving away from me? Is it moving towards Bristol? Is it moving towards Johnson City? Which way is it going? And so that brings us to the word velocity, which is extremely important. Think about that in terms of weather, whether it's a thunderstorm or a blizzard or rain, whatever it might be. We want to know the direction of things. And so meteorologists obviously are very dependent on velocity. And so velocity is just speed with a direction. But there's also some other important differences as well. So in your scientist notebook, what you want to do is go to a clean page and write the word velocity at the top. And we'd actually like you to write all of the words on this slide. And remember, you can pause the video if you need to. So velocity just describes motion, again, just like speed does, but this time it's speed with a direction. And that means that when I want to describe velocity to somebody, I need a couple of things. I need a number. I'm still going to have a number. And the word we use in physics and in science to describe a quantity that just has a number is scalar. That's kind of a weird word, isn't it? But that means it just has a number. But because velocity also has a direction, I need a way to represent that as well. And the way that we represent direction in physics is by using something called a vector. And it is just an arrow. I've drawn an example of one right here. And actually, the length of the arrow will indicate some different things for us as we use vectors in forces later. So because velocity has a direction component, we call it also a vector quantity, because we're going to use arrows with it to indicate direction. Here's some examples of what velocity might sound like and how it sounds different than speed. And if I was doing my notes, guys, my doodle notes, I might make these a different color, just like you see right here on the screen, or you could highlight them. So if I have something that is going 20 miles per hour north, I know that is telling me a velocity. See what a difference that makes? Now I know not only the speed, 20 miles per hour. Okay, there's my distance divided by my time, but I know which direction this object is going as well. So here are two other examples, and write the examples down. So 5 meters per second east, 80 kilometers per hour southwest. All of those would be velocity. There's another important difference with velocity. And we're going to go ahead and introduce this to you. Although, honestly, guys, we have noticed that sometimes you will see as we move into graphs and things that often we will use speed and velocity kind of interchangeably. We get by with that because of the way things are graphed. I don't want you to get overly concerned about it, but we do want to make sure you know that technically velocity depends on something called displacement. And displacement is different than distance. Remember, speed depends on distance. Velocity actually depends on something called displacement. So here's the difference. If this, we'll pretend this is a car right here, and I decide that I'm going to get in my car and I am going to drive to Johnson City. All right, I'm going to drive to Johnson City. So I get in my car, and first I decide that I'm going to go, I'm going to pick up Miss Pearson. And so I drive over there, and now we're kind of driving along. Oh, and then we decide, let's get Mr. Way. Let's take him too. So we'll go over there and get Mr. Way, and now we'll get in our car and make it to Johnson City. Well, my car traveled this whole path. And so whatever many miles that is, that would be my distance. That's the length that the object actually traveled. Displacement's different. All I care about with this word displacement is a straight line path that tells me the difference in the object's starting point and ending point. So if I drew a straight line from my house, this is where I started, over to wherever I went in Johnson City, this is displacement. We have a short video that you need to watch on the difference in distance and displacement, but here's a really good example to show you why it matters, okay? So let's pretend we've got a peacock. I have no clue why I made this up last year with a peacock, but we've got one. We have a peacock. And our peacock is going to start right here at point A and walk in a rectangle. And I don't know why. My peacock is just doing that. And so off goes my peacock. 4 meters in this direction, and then 2 meters down here. And maybe, I don't know, maybe he sees some food over there. So 4 meters here, and then 2 meters back to his little peacock house. All right. Well, if I wanted to figure out the average speed, which is the total distance divided by the total amount of time, I can do that. 4 plus 2 plus 4 plus 2 is 12 meters. That's the total distance. And the total amount of time, it says in the problem right here, was 6 meters. 12 divided by 6 is 2. So the average speed of my peacock is 2 meters per minute. Okay, that's fine by me. I don't know. Maybe he's just eating food along the way. But what if I want the average velocity? Well, now that's completely different, because look what happens. I want to use displacement. Now let's look right here. If he starts at point A, and I said displacement is the difference between, in this case, where my peacock starts and where my peacock ends up. Well, look, if he walks this path and ends up exactly where he started, I mean, we're going to say exactly where he started, then he has a displacement of 0. And 0 divided by 6 is still 0. That's a little freaky, I know. But we wanted to go ahead and technically point out to you that there is a difference. There is a difference between speed and velocity, and it has to do not only with direction, but technically with what we're using to calculate. We want you to add this chart into your notebook. So just make a T chart, and this is speed versus velocity. And this kind of helps summarize what we've talked about so far. Speed describes motion, and it just describes how fast an object is moving. Velocity also describes motion, but it's describing how fast and in what direction an object is moving. Speed is what we call a scalar quantity, which means it can be represented by a number only. Velocity needs to be represented by a vector because it's got a direction component. Remember, for us, a vector quantity will be something that we will draw these arrows with. You'll see us drawing a lot more arrows as we move into forces. Speed depends technically on distance. Velocity depends on displacement. So if I really want to accurately represent speed, I would use distance and time, but if I want to accurately represent velocity, I would technically need displacement, time, and direction. So make sure you get this in your notes. We wanted to show you not only meteorologists or weather people, but pilots also depend on velocity. We wanted to kind of give you an example of how those vectors can look. If you're in a plane and this blue represents the velocity, okay, traveling this direction, right? This direction. If you have a little tailwind, and that's a wind that is pushing behind, kind of helping the plane go faster, look what happens. If I let the red represent the velocity of that little tailwind, okay, I know it's technically behind there, but we put it up here. Look at this plane, it gets there a little bit faster. If this plane, you notice, still has the vector representing velocity, but look what happens. Now it's got something called a little headwind. And that little headwind is represented by that little red arrow vector, but it's pushing against the direction. It's pushing in the opposite direction that the plane is trying to travel. And look what happens to my little middle plane. Slows down a little bit. I don't get to travel in a plane a whole lot, but when I do, I like when the pilot comes on and says, yes, we've got a little tailwind that's going to help us out here, because I know that that's going to help me get where I'm going a little bit faster. But look at this. What if you're in a plane and you're coming in for a landing and your runway's right here? It's in the middle. But as you're landing, now look at our little red vector. Here's blue is still the velocity of the plane. It's coming this way, but there's another little vector right there. Look at that little red vector that representing the crosswind. What happens to my plane down here? Going to miss the runway. So pilots are also very concerned, yes, with speed, but they also understand the difference in speed and velocity. So at that point in your notes, at this point, all you need to do really is just briefly summarize your notes on velocity. Make sure you write the definition, and then make sure you're comfortable and you could explain the difference between velocity and speed.